Good morning, students. I am Dr. Rajwant, lecturer chemistry, Government Polytechnic College for Girls, Amritsar. Our today's topic is types of chemical equilibrium. But before discussing various types of chemical equilibrium and the expression for the equilibrium constant, we must know what is a reversible reaction. Now, reversible reaction, we come across large number of reactions in which there is both a forward and a backward reaction taking place at the same moment. Now, the reactions in which the reactants give us the products, that is known as the forward reaction, and the one in which the products give back the reactants, that is termed as the reverse reaction or the backward reaction. Now, equilibrium can be established only in case of reversible reaction. The irreversible reactions, the ones in which the products cannot give back the reactants, they can't exhibit this state of equilibrium. Now, when we say that reversible, we can come across equilibrium in case of reversible reactions. Reversible reactions can only show a state of equilibrium if the system is closed one. Now, in this slide you are observing two examples. The first one, in which a single arrow is used, predicts an irreversible reaction in which the sulfur dioxide is reacting with oxygen to give you the sulfur trioxide. Now, when this reaction is carried out in an open container, open system, then the sulfur trioxide such produced cannot give back sulfur dioxide and oxygen back. On the other hand, if the same process is carried out in a closed container, we observe that as soon as the sulfur trioxide gas is produced, it dissociates back into sulfur dioxide and oxygen gas. Now, initially graphically we can represent a chemical equilibrium as the state at which the rate of forward reaction becomes equal to rate of backward reaction. Now, what do we mean by this, that rate of forward reaction becomes equal to rate of backward reaction? By this we mean that how much number of moles or the molecules of reactants get converted into the products, the same amount of the product give back the reactants in the same time. Now, in order to establish an expression for equilibrium constant, we must know on which factor the rate of a reaction depends. Now, in order to derive the relationship for the rate of reaction, we must understand law of mass action. Now, law of mass action states that the rate of a reaction, the rate at which the reactants get converted to products, the rate of the reaction is directly proportional to the product of molar concentration of the reactants, with each concentration term raised to the power equal to the corresponding stoichiometric coefficient which appear in the balanced chemical equation. Now, this law of mass action was given by Goldberg and P. Wege. As you can see over here, that according to this law, the rate of a reaction is directly proportional to the active masses or we can say the product of molar concentration of the reactants with each concentration term raised to the power equal to the corresponding stoichiometric coefficients which appear in the balanced chemical equation. Now, this rate which we are determining as the product, it can be had only at constant temperature and pressure. Means when the temperature and pressure is kept constant, the rate of a chemical reaction is directly proportional to the product of molar concentration of the reactants. Now, graphically, chemical equilibrium is represented as initially when the time is 0, we are only having the reactants, only the forward reaction is taking place, but this goes on decreasing with time, and as the products are formed, the rate of the backward reaction goes on increasing. But a stage comes when the rate of forward as well as the backward reaction that becomes constant. Now, this state at which the forward and the reverse rates become equal, this is known as equilibrium. Now, this state is observed as, we can define equilibrium as the state at which the measurable properties of the system becomes constant. Now, when we say measurable properties of the system becomes constant, by this we mean the temperature of the system remains constant, the pressure remains the constant, concentration of all the reactants as well as the products becomes constant. So, we can assume that no reaction is taking place, but actually this is not the case. At equilibrium, both the reactions forward as well as the backward are taking place, but at the same rate. Now, this example is for a general reaction in which the reactant A reacts with the another reactant B to give us the product. Now, the rate at which A reacts will be directly proportional to its active mass or the molar concentration of A. Now, these square brackets in which the reactant is enclosed, it represents the molar concentration. Similarly, we can say that the rate at which B reacts, that is directly proportional to the active mass or the molar concentration of the reactant B. If we want to say that the rate at which both and A and B react together, then that will be proportional to the product of the concentration of both the reactants, that is A and B. Now, if we remove the sign of proportionality, then it can be equated as K into A into B, that is the concentration of the reactant A and the concentration of the reactant B. Now, here K is constant of proportionality and it is called the rate constant. Now, for a more general equation in which the number of moles of the various reactants, they are different, which can be represented as A moles of A reacts with B moles of B and C moles of C to give us the products. In this case, the rate of the reaction is directly proportional to concentration of A raised to the power A, concentration of B raised to the power B multiplied by concentration of C raised to the power C. Now, here A, B, C, they are the stoichiometric coefficients of the respective reactants in the chemical equation. So, this is according to law of mass action. Now, if we remove this sign of proportionality, then the rate of reaction, the expression for the rate of reaction can be written as Kc, sorry, this is equilibrium constant Kc, which will be equal to the ratio of the product of the concentration of the products to the product of the concentration of the reactants with each concentration term raised to the power equal to number of moles of that component or the stoichiometric coefficients of that component. Now, for a reversible reaction represented by A plus B, in which A and B are two reactants that are giving us C and D, the two products. In this case, the rate of forward reaction will be proportional to the product of the concentration of A and concentration of B. Now, if we remove the sign of proportionality, then it will be equated as Kf into concentration of A into concentration of B. Here Kf is the rate constant for the forward reaction. Similarly, when we consider the backward reaction, for the backward reaction C and D, both the products will act as reactants, then the rate of the backward reaction, that will be proportional to the concentration of C and concentration of D, that means the product of the concentration of these two products. Now, if we remove here also the sign of proportionality, we get Kb into concentration of C into concentration of D. Now, here Kb is the rate constant for the backward reaction. Now, as we have already discussed that at equilibrium, the two rates, that means the rate for the forward reaction and the rate for the backward reaction, they becomes equal. Now, if we equate the two expression, we achieve at Kf into concentration of A into concentration of B, that is equal to Kb, that is the rate constant for the backward reaction, into concentration of C into concentration of D. Now, on rearranging this equation, what do we get over here is concentration of C into concentration of D upon concentration of A into concentration of B, that will be equal to rate constant for the forward reaction upon rate constant for the backward reaction. Now, since these two are constant, their ratio will also be constant, which can be represented as K. Here K is the equilibrium constant. Now, for a more general reaction in which the number of moles of the various reactants, they are different, then the equilibrium expression for that reaction, general reaction, can be written as shown here, in which A moles of A react with B moles of B to give you C moles of C and D moles of D. In this case, the equilibrium constant Kc, that can be written as the ratio of the product of the concentration of the products to the product of the concentration of the reactants, with each concentration term raised to the power equal to number of moles of that component or the stoichiometric coefficient of that component in the chemical equation. So, we can say that for any type of chemical equilibrium of the type, the following is a constant at a given temperature T. Now, as we vary the temperature, the value of the equilibrium constant will change. Now, value of equilibrium constant does not depend upon the initial molar concentration of the reactants or the products. Now, regarding the properties of an equilibrium, when we say that the equilibrium has been established in a reversible reaction, what do we mean? We mean that the concentration of the reactants and the product has become constant, means at equilibrium there is no change in the concentration of the reactants and the products. Now, the second characteristic or the property of an equilibrium is that equilibrium is dynamic in nature. Now, what do we mean by this dynamic in nature? It means, no doubt to us, it appears to be static, means there is no change in the concentration, no change in the temperature, no change in the pressure or the other measurable properties, but still the reactions are taking place, means the reaction is not static, the equilibrium is not static, it is dynamic in nature. The only thing is that the forward and the backward reactions, they are occurring at the same rate As a result, to us, even at the macroscopic level or microscopic level, it appears that the equilibrium state of equilibrium is static, but when observed on a molecular level, it is dynamic in nature. And the another system, another property, as I have already discussed with you, that equilibrium can only be attained in a closed system. Now, if the products are allowed to leave the system, naturally the backward reaction or the reverse reaction will not be able to take place. Now, if that is not taking place, naturally the equilibrium can't be established. So, we can establish equilibrium in case of reversible reactions only in a closed system. Now, another characteristic or another property of the equilibrium is that it can be attained from either direction. It means whether we take the reactants and we take the products, the same equilibrium will be established in the same moment, provided all the other parameters they are kept constant. Means it does not matter whether you are starting with reactants or with products. The only thing that will happen will be the value of the equilibrium constant will be just the reciprocal of the previous one. Means if we are taking the reactants first and establishing the equilibrium constant, then let its value will be Kc, and on the other hand, if we start with the products and establish the equilibrium, in this case the value of the equilibrium constant, new equilibrium constant, will be the reciprocal of the previous one, that is 1 upon Kc. Another characteristic of equilibrium is that a catalyst does not alter its position. Now, when we say that catalyst does not alter its position, it means catalyst does not have any effect on the equilibrium, on the state of equilibrium. The reason behind is that catalyst affects the rate of forward as well as the backward reaction to the same extent. Now, when the rate for the forward as well as the backward reaction is being changed at the same rate, it means the state of the equilibrium will not be disturbed. The only thing which happens on adding a catalyst to a reversible system is that it helps in attaining the equilibrium fast, because both the reaction forward as well as the backward, they are taking place now at a faster rate, you can say. Now, their rates are changed to the same extent, it means the position of the equilibrium is not altered. On the other hand, it can be attained earlier. Now, what is the meaning of K or the equilibrium constant? Now, equilibrium constant can tell us if a reaction is product favored or reactant favored. Now, how it happens? For example, consider this example of the preparation of ammonia by Haber's process from nitrogen and hydrogen. In this case, the expression for the equilibrium constant can be written as concentration of ammonia raised to the power 2 divided by concentration of nitrogen into concentration of hydrogen raised to the power 3, and its value for a particular concentration is given as 3.5 into 10 raised to the power 8. Now, this value is quite high, more than 1, or you can well observe that it is having a very higher value, 10 raised to the power 8. It means this identity is having a higher value as compared to these. It means this reaction is product favored, means the concentration of the product is more. Now, concentration, higher value of Kc predicts us that the concentration of products is much greater than that of the reactants at equilibrium. So, we can say the reaction is strongly product favored, means higher the value of the equilibrium constant means the reaction is product favored. Now, how the magnitude of equilibrium constant and the equilibrium concentrations are related. When the equilibrium constant is large, the concentration of the reactants are small as compared to the products at equilibrium, or we can say the equilibrium favors the products. So, this can be animated in this form. Now, here the large value of Kc shows that the concentration of products is much more than the concentration of the reactants. On the other hand, a lower value of the equilibrium constant means the rate of forward, when the equilibrium constant is 1, it means that the forward and the rate of the backward reaction, they are equal, but it does not mean that the concentration of the products and the reactants, that is to be equal. That is not required to be equal, and it is rarely equal at equilibrium. Now, when the equilibrium constant is small, means the value is of Kc is less, it means the concentrations of the reactants are large as compared to the concentration of the products at equilibrium. It means the equilibrium favors the reactants, not the products. Now, this can be animated as the small value of Kc predicts larger concentration for the reactants as compared to the products. Now, coming to types of chemical equilibrium, there are basically two types of chemical equilibrium. One is the homogeneous equilibrium and the other is heterogeneous equilibrium. Now, what do we mean by homogeneous equilibrium? When an equilibrium reaction, all the reactants and the products, they are in the same phase, whether gaseous or liquid or solids. When all the reactants as well as the products, they are in the same phase, then such an equilibrium is termed as homogeneous equilibrium. The examples of the homogeneous equilibrium you can see over here. The first one is the Haber's process for the manufacturing of ammonia, another is the manufacturing of sulfur trioxide, and the last reaction is the esterification reaction between ethanol and acetic acid. Here, I am sorry, there is one C extra over here. It should be CH3COOH, resulting in the formation of an ester and water. Now, in this case, you can see all the reactants as well as the products, they are in the liquid form. On the other hand, in the previous two examples, all the reactants and the products, they are in one phase, that is the gaseous phase only. So, these are the examples of homogeneous equilibrium. Now, heterogeneous equilibrium is the one in which one or more of the products or the reactants, they are present in two or more phases, means either one of them or more of them, they are solids and the remaining are in the gaseous state or in the liquid form. Now, here are certain examples for the heterogeneous equilibrium. The first one is the decomposition of calcium carbonate to give us calcium oxide. Both these, one is the reactant calcium carbonate as well as the product calcium oxide, they are in the solid state. On the other hand, carbon dioxide, one of the products, that is in the gaseous state, means there are two different phases over here. Similarly, in the next example, the decomposition of sodium bicarbonate to form sodium carbonate, carbon dioxide and water. In this case also, bicarbonate as well as carbonate, sodium bicarbonate and carbonate, they are in the solid phase. On the other hand, water and carbon dioxide, they are released in the gaseous form. Now, the third example is for the physical equilibrium, representing the vaporization of water, in which the liquid water and the gaseous water, they are in equilibrium. And the third example, fourth example is the ionization of calcium hydroxide, resulting in the formation of calcium ions and hydroxyl ions in the aqueous medium. Here calcium hydroxide is in the solid phase. So, we can say that an equilibrium in which all the reactants, they are in the same phase, that is termed as homogeneous equilibrium, On the other hand, the one in which there are two or more than two different phases, then we say it to be heterogeneous equilibrium. Now, what is the relationship between the magnitude of equilibrium constant and the equilibrium concentration? When the equilibrium constant is about 1, the concentration of the reactants and the products are about equal at equilibrium. So, animatically and through animation we can say that when Kc is about 1, it means the concentration of the products and the reactants, they are same. Now, how can we measure Kc values or the equilibrium constant values? There are basically two units, because we can measure the concentration either in moles per liter for solution or in terms of pressure for gaseous. If we have the homogeneous system in which all the reactants or the products, they are present in the gaseous state, then we can use pressure or atmospheres for the concentration. It means there are two unit systems which are possible for measuring the values of the equilibrium constant. Now, the first is when the concentration is measured in moles per liter, then the values of the equilibrium constant Kc, they are in terms of molar units, and the constant is referred to as equilibrium constant for concentration units, that is moles per liter. On the other hand, when the concentration of gases is measured in pressure units, then the constant is referred to as Kp instead of Kc. Here P is for pressure units, that is atmospheres. Now, the relationship between Kc and Kp can be represented like this, that Kp is equal to Kc into R into T raised to the power delta n. Now, in this equation, this R is gas constant and its value is 0.0821 atmosphere liters per moles per Kelvin. T is the temperature in the Kelvin scale, and delta n is the difference in the number of moles of the gaseous products and the number of moles of the gaseous reactants in the balanced equation. Now, when the number of moles of the gaseous product and that of the gaseous reactants, that becomes same, if that is same, then delta n will be 0. In that case, Kp will be equal to Kc, because anything raised to the power 0 is equal to 1, then the Kp, that is this equilibrium constant in pressure units, that will be equal to Kc, that is the equilibrium constant in the concentration unit, that is moles per liter. Now, this is another example for converting the Kp and Kc values. For this equation in which the ammonia is formed from nitrogen and hydrogen in a homogeneous equilibrium, the value of Kc at 472 degrees Celsius is given as 0.105 at 472 degrees Celsius. We have to find the value of Kp. Now, in this case, how can we find? We know that Kp is equal to Kc into R into T raised to the power n. Here we know R is a constant and its value is 0.0821 atmosphere liters per mole per degree Kelvin, and T, as the temperature is given to be 472 degrees Celsius, we have to convert it into Kelvin scale. We have added plus 273 over here, so that the resultant is 745 Kelvin. Now, in this case, delta n, that is the difference in the number of gaseous moles of the products and the reactants. On the product side, we are having 2 moles. On the other hand, on the reactant side, we have 1 mole for nitrogen and 3 moles for hydrogen, a total of 4. Now, subtracting 4 from 2, we get minus 2, that is delta n. The value for delta n is minus 2 over here. Now, substituting the various values, we can find out the value of Kp like this. Now, chemical equilibrium is also established in the ionization of weak electrolytes. Now, before we discuss the equilibrium constant for the ionization of the weak electrolytes, we must know what are electrolytes and non-electrolytes. So, generally a substance which conduct electricity either in the molten state or in the solution form, for example acids, bases and salts, such substances they are termed as electrolytes. On the other hand, there are substances which do not conduct electricity either in the molten state or in the solution form, means they are non-conductors of electricity, they do not conduct electricity. So, such substances they are, the examples of such substances are sugar,